we do a similar analysis as we did yesterday for the Basper Valley to get an understanding of the slope and the shape of the profile. And then we use the same field area and go into Matlab and perform a forward evolution modeling of how that landscape would evolve. I have put a few things on GitHub that may be of interest to you. The first thing is that there is a new Matlab code that focuses on the Basper. It's a river in the northwestern part of the Himalaya. It's a tributary of the Sutlej River. And I put 2 DEMs on there. One DEM is from the SOTM data that we used yesterday as well. And another DEM is from the ALOS 12.5 meter data. This is now freely available data since last fall. I just downloaded this morning, and we can have a quick look at it to see how these data compare to the SOTM data and what data quality is there, because this is now also available for the Himalaya. Maybe as a quick addition for those of you who are really into the high resolution stuff, and I wanted to say this yesterday already, but I didn't end up doing it. I wanted to show that there is a so-called high resolution DEM available for the Himalayas, made up out of stereogrammetry. And I am just showing you a quick tile here for the area. Unfortunately, this is not a continuous DEM because the optical stereogrammetry does not always work out. But for some areas, there is very, very good coverage. These data are being produced at 1 meter spatial resolution. And then they are upsampled to 8 meters. So this is an 8 meter DEM for the Western Himalaya, parts of it at least. So this is the river that we will be focusing on. I just wanted to point out there is something that is called the Arctic DEM, and that is derived from a set of GeoEye and worldview imagery. And these are very, very high resolution data that have been originally created for the glaciological community. So they're looking at mass balance changes, but the byproduct is a digital elevation model for most of the Himalaya.
So which data is this?
Arctic DEM.
Oh, Arctic DEM is 80 meters.
So this is what I was just talking about. So I just wanted to point out we can't use those data for the tectonic geomorphology analysis because they are not continuous, but these may be some very useful data for some of you. It depends where you are located at. The central part of the Himalaya is much better covered than the western part of the Himalaya. Okay, the idea is that you could open up, bless you, that you could open up the file that I'm providing for the Basper Valley. If you go on, let me show you, if you go on GitHub, if you go on GitHub into the Matlab topo tools, you will see that there is a DEM called ALOS 12.5 meters resolution. There is a DEM called Basper SOTM1 30 meter spatial resolution. That's the same one that we used yesterday. And then there is a Matlab file called Basper steepness indices, okay? And that's something that we are going to work with, okay? We are going to use this, and we do a quick analysis of the Basper, building upon what we did yesterday with the steepness indices, right? So that we have a better understanding of what that is like. Okay, you know the drill. Open up Matlab, navigate to the directory, and add the path and all this stuff, right? So, so if you look at if you do this analysis, oh no, I'll wait till you guys are there. Are you interested in, should I do this, or would you like to do it too? No, you should do it too, right? Okay, let's wait here for a few seconds. Oh, I'm just realizing there's a little error in here that I had. There's one line that needs to be just, so that plot may not work out, so you may have to change the plotting may not work out, so you may have to comment this out. I will give me a second. Okay, I just have re-uploaded that code. I'm sorry, I had one typo in there. There was one tiny mistake with the figure. If you re-download the Basper steepness indices, that should have that typo removed, okay? It was essentially just the first figure. It was just making about a figure. It didn't have any other... So whenever you are ready, we can talk about this.
The Basper DEM, 12.5 meters, is it a reference to the geoid level or ellipsoid?
It's a standard ALOS data. It needs to be corrected for a geoid. It's not has been corrected yet. So we couldn't compare the absolute elevations to the SOTM. But the relatives elevations should work well. And since we are interested in slope, and slope is a relative value, it should give similar results. Yeah. So can I help with anything? Are you able to load in the DEM and do the first step of displaying the data? So we're going through the simple steps of doing the flow direction, right? Do the flow accumulation, and then we extract the river network. So that will be the, on the right-hand side, we have the first figure, which is the flow accumulation. So that's a logarithmic of it. So we have 6 orders of magnitude available here. I chose 1 square kilometer as a drainage area threshold, okay? So this is the threshold above which we have then the channels. This is a network that I then have extracted. You notice immediately you have the Sutlej. This is a big river flowing here. This is a part of the Sutlej, and that is the tributary that we are now looking at. So the Baspa stretches from glacially influenced areas up at 5,000 and 6,000 meters down to roughly 2,000 meters where there's a confluence with the Sutlej River. When you do the plotting of the longitudinal river profile, you see that there are essentially 2 profiles in here. This is the trunk stream of the Baspa, but you also see this guy in here, which is essentially the profile of the Sutlej, okay? So you follow the Sutlej and then you go up the Baspa. And we don't want that, right? We only want to have the Baspa. So I put in a few lines of code. So I essentially zoomed in here. I zoomed into this area, and I clicked the location of the outlet of the Baspa. This is the outlet. And I used this coordinate here, the minus 91,000 and so on, to identify the drainage basin. So I'm using this coordinate to clip out a drainage basin that is only the Baspa. Because most of the times when you generate a DEM, the clip is much larger than the catchment that you're interested in, so you need to tailor it down to the area that you're interested in. And one way of doing that is by just clicking to the outlet. An alternative option could be you have a GPS coordinate from the field. You could put that in there then too. You need to convert the GPS coordinate into a UTM, but that will be the step to do. Okay, so this is a straightforward way of focusing on the catchment. And if we are running this, we are getting the following nice plot. So now you see it's only the black catchment here that is the Baspa River. Now we are only focusing on the Baspa. We have removed this line here from the Sutlej Valley because we have clicked the drainage point. And then we can plot the longitudinal river profile in the same fashion as we have done yesterday. Being a geomorphologist or a tectonic geomorphologist, you already see some major nick points in here, right? So there are some really major nick points in here. You go up from what is it, 1,800 meters. You go up and you have a major nick point in here. This is a large landslide. This is a Holocene landslide that dammed the river and created a big lake after it. and then this lake has been drained about 6,000 years ago. So this was a lake that I did my PhD on, by the way, about 20 years ago. So I spent a lot of time working on this lake. And then if you continue, you see another nick point in here. This is another big landslide. That's another big landslide that went into the river and dammed the river for a while. It's a Holocene event. So this is this nick point. And up here is another nick point. That is also a landslide. So there have been major landslides that went into this river, and they have consecutively dammed the river. So those 1, 2, 3 nick points are related to landslides. And then we have a long, long stretch that looks pretty stable. And here we have another nick point here, and these are above 4,500 meters, and this is a glaciated terrain that was glaciated during the Holocene. So just by looking at this profile, we already can tell some of the processes that occur. The reason why I pulled out this Basper Valley is because we can determine the steepness index for this, and this is one of the nicest examples why that assumption of the normalization factor theta equals 0.45 is not working well for those tectonically active regions. And you will see in a second why. Before we continue, is everybody roughly there, or should we wait more time? What's the general consensus?
We need to open that LOS.
You say what? I need my memory stick. Here we go.
Check my Matlab.
Yeah. So again, we are masking out the BASPA, and then we can plot the log area, log slope plots for this region. And we are doing this because when we then use LandLab, we will do exactly the same using the model output from LandLab afterwards, okay? Should I wait a little more? Yeah, okay, yeah, sure.
We are taking this SRTM file now, and I have opened this folder also. It's showing.
Well, you need to do the add path, then this didn't work out.
Yeah, I added it.
Then this didn't work out.
And just again
Okay. No, do try it. I thought that you select the board. Then this is not working. then the path is wrong or something. I don't know. Check that this is the correct path.
Okay, where I've kept the TIFF file, it should be the partner. Is that so?
I don't know if this, you need to check if this is the correct path.
Path should be the one where my TIF file is there, no?
Where you have the topotool, I don't know where you have stored it, yeah? But this is not working. That's the command that is not working. So it's not finding the.
This is.
No, not this one, the other one. This one, yeah.
Oh, yes.
That is the one, right? And that's not in here. That needs to be in here. That's this. That's the path. Yeah? You had a.
So actually, I don't get it. How to remove this?
That's the next line where we do the where we click the outlet point and then we do the drainage basin. That is the next in the next line. Here, this is where we do the drainage basins. I get the coordinate from the file, and I essentially only use everything upstream from that point. So that's the new drainage basin that I generate. So that is this line. So if you run this, then you have it clipped to a smaller region. Okay. I just wanted to briefly talk a little bit about, let me see if I can open up both of the figures. So now we talked about the steepness index yesterday, right, and fitting the regression in log space. If we allow the fit to fits the y-intercept and the slope, so the way that, giving it all the flexibility, we see that we obtain a theta of 0.28. Meaning you get a much flatter concavity than you would expect. And part of the reason for that is that we have multiple landslides in there that essentially prevent the river from incising into that section. So you get a different concavity than what you would expect from a bedrock river. Okay, so that's an interesting observation because we have those landslides throughout the entire Himalaya, right? So we know that, right, that we have landslides throughout the entire Himalaya. So that also that notion here that a global average of 0.45, that's globally used. For the Himalaya, you probably may want to reconsider this. Maybe the rivers have a different character in the Himalaya. So that's something just to point out. And Would you like to have some more time, or should we talk about some of the results? Okay. So I just wanted to point out some additional steps on top of what we have been doing yesterday. And here's a map of the river steepness using the normalization factor of 0.45. And you can clearly see the steep tributaries that come in of the Baspa, and how it flattens out in the top part because we have glacial terrain in there, right? So this is part of these approaches. I wanted to show you that sometimes it's nice to just look at the trunk stream. You know, sometimes it's helpful to say, let's not worry about those tributaries too much. Let's focus on the trunk stream. And this now is a plot that only uses the trunk stream. And the way I have done this is in the analysis, I am just calling the gradient and the drainage area. I'm just calling this for the trunk stream. The command trunk extracts the longest stream from a river network, as we have talked about yesterday, right? The longest path. So you can separate essentially the trunk stream from the tributaries, and that allows you to do the plot. And let's look at this for a little bit. So we have this guy here, and now I'm getting the longitudinal river profile again. So I'm moving this here. Let's see how I do this. So here you see the river coming up from near the junction with the Sutlej, and here we see how it goes steeply up, right? You see the red colors in here. That is this steepness, right? This steepness, that high slope in here, is this first red color. And then we have very low steepness indices. These low steepness indices refer to this flat area, okay? And then we have another steep area here indicated in orange and red. That is a second nick point. And then we see there is another nick point following here. This is the next one. So these are those nick points, those high steepness indices that we find in map view here. And then we have the relatively continuous, you know, here and there, when a tributary comes in and brings in sediment sources, the slope of the river changes. We see that variation along the channel. And then up here, we see how things flatten. This is how things flatten. This is this area here where you have the glacial erosion that took place and essentially made the valley much more flat, okay? So this is, you can nicely pull this out here. And then this is another part of the glacial terrain. Yesterday we used chi plots. Let's go into the chi realm and let's look at what this would look like in the chi world. So this now I'm going to get my river profile. Okay, you're now familiar with reading these plots, right? We have on the y-axis, we have chi distances. On the y-axis, we have elevation. On the x-axis, we have chi distances. And anything above this average line here indicates the river is a little steeper than usually, right? So here we have great steepnesses, and the steepness is going down here, and then we have lower steepnesses. So you can look at this at several wavelengths of nick points. We have one large-scale wavelength in here that essentially reaches over a longer distance, where we have a shape like this, and then at the top part, a shape like this. And on top of this larger wavelengths, we have those really pronounced nick points that are associated with the individual landslides that we looked at. Or that I have explained before. So those guys here, this, and this, these are those pronounced kinks in that profile. So if we were going to take the slope of this line, of this black line, wherever the change is very, very rapid, we would essentially have a nick point finder. And this is what those algorithms do. Algorithms that automatically try to identify nick points, they look, for example, at the slope of this line. And this is what we've done in the Al-Neely paper, in the 2017 paper, but others have done this for other regions as well. So usually, or you can use the chi plot to identify nick points in a very efficient manner because you can just take the derivative of this line, and that tells you where this line is rapidly changing, something weird is happening, right? You need to identify a length scale over which you take the nick point, over which you take the derivative, but in generally speaking, you are able to use these data to identify nick points very, very efficiently, okay? Are there questions? Should we discuss this any further? What is it, what you say? Yes?
So the landslide, the first is counted. The first nick point, you said there were landslides.
You mean 1, 2, 3, 4?
The first one.
The first one. Yeah.
You indicated there were landslides.
That is a big, big landslide. Yeah. In fact, when you would go to Google Earth, let me just see if I can do that here. Let me just hold on a second here. I need to. So. Just see how we can get this. Oops. Yeah, here you can maybe see it. Yeah. So I'm looking at the Baspa River. So I'm looking at the Sutlej is down here. We are going up the Baspa River. And here at this area, you see these deposits sitting here. This is a big, big landslide that is now being incised. Upstream, you have lake sediments that formed a nice flat surface, and this is where a hydropower company also put up a hydropower dam because it's a nice flat area. So this is the Baspa hydropower project. But that first nick point from down here to up here, you easily make a few hundred meters elevation gain over a very, very short distance because you're essentially going from the bottom of the landslide to the top of the landslide, which is that pronounced nick point that we see in the steepness indices plots. Yeah.
If we can correlate the nick points to the landslide, so all nick points will not have...
Nine. No. Let me point out, it would be nice if that would be the case, but that is not the case. Let me just point out the different nick point types that exist. And here in this paper by Al-Neely, we have made a plot to characterize some of the different types of nick points that exist. And you talk about a nick point or a nick zone. If you have a long wavelength deformational signal, for example, you have a couple of faults that would drive up a structure. So if you have a, if this is a river going down the mountains, this is distance, and this is the height. And you would have structures that bring up part of the landscape, and the river does something like this. You would have a Nick zone, something that is warped over a longer time scale. This is very typical for the seawallics or the frontal regions where you have potentially multiple splay faults that generate a larger deformational zone. So this is something that is called a Nick zone, and this is something that we have called like this, a Nick zone that would have a specific signal in a logged area log slope plot. So this is how we then translated this into a log drainage area log slope plot. If you have something that is more related to a landslide, you would have a much more rapidly declining. You see the convexity of this is different, right? This is more concave, this is more convex, right? So this is something that is related to a landslide where we would then see, for example, a step in the Ks values. And this is exactly what we see in our plot here. So this steepness change going from this area down here, from the low slope areas to the steep areas, is exactly that jump that you see in the log drainage area log slope plot. Okay? So you see that KSN that has a different y-intercept, you would see that in here. And then you have another type of Nick point that is sometimes associated with landslides, but most often associated with hanging valleys, for example, that are prominent, very prominent in the Himalaya as well. So those hanging valleys potentially formed through rivers that did not keep up with the incision of the main river. So they formed waterfall. Essentially, every waterfall that we observe in Hawaii or in the Himalaya, they can be characterized by this vertical step Nick point. So you essentially have a concavity, and then you drop down in this part. So this is a diffusional process that occurred here, and then you have the waterfall. And they would look something like this in a log slope, log drainage area plot, okay? So these are different types of Nick points, Nick zones that can be associated with different processes. Not every Nick point that we see in a steepness index plot is actually related to a landslide. But if we know that we are in the Himalaya and we have a spatial understanding of the size of that Nick zone, then yes, you know, it's likely that it's a landslide. Let's put it that way. You know, we would not, or I should say, some people in the field, or some people that have not been to the field here, they could also interpret this as being a thrust fault, right? You could also say, here's a thrust fault that brought up this part. You have a steepened section and a flatter section, but that's not the case. Yeah, so you know, that's when field work comes in handy, so that you can actually say that this is a landslide that has caused that signal. Yeah, and just as an additional piece of information, we talked about the chai plots.
Why we are getting that landslide over there? Why we are getting that landslide, such a big landslide at that particular location?
Well, you know, no one really knows, because no one has been there 8,000 years ago when the landslide was triggered. But the general idea is that this was in the intensified monsoon phase, when there was much higher rainfall on the Tibetan plateau and also in the northwestern Himalaya. So it was much wetter, and that changes the pore pressure of the rocks, and that essentially changes the friction coefficient, so you can trigger landslides more easily. So my interpretation is because we have this cluster of landslides between 9 and 6,000 years ago, that this is essentially a climatic signal because we had a much more intensified rainfall during that time that changed pore pressures that allowed those landslides to be triggered. And these were really big landslides. You know, I'm not talking about some small surface movements of 5 meter thickness. I'm talking about a landslide with several 100 meter thickness. So all of those 3 landslides that I've talked about, they exceed 1 cubic kilometer. So these are really, really big landslides. And the idea is that climate has played a role in triggering this.
So in 10,000 years, it's still there. It is like...
Well, I mean, the lake existed for roughly 2,000 years. So you can envision that when you have a river profile that looks like this. This is the river profile prior to. This is distance. This is height. So this is the river profile prior to the landslide. If you now have a landslide essentially acts as a dam, right? A landslide closes the river. There is no water, almost no water going through, definitely no sediment. So you start up filling up the landslide. You start filling up behind the landslide. So you now have sediment sitting here, right? So you fill up that area behind the landslides with sediment, and eventually that tiny little intramontane basin is filled up with sediment, and the water overtops. And then the water overtops and starts to incise again, right? And this is exactly what we see. We see that this nick point started or is having, let me see, where is it? Where is it? Here. You know, here at this part, this is now, well, at this level you can barely see it, but believe me that this is a nick zone that has been slightly backward eroded already. So parts of the sediments that were deposited in the Holocene have already been incised. So we know that those sediments are roughly 4,000 to 5,000 years old. These are the lake sediments, and they are currently being eroded. So in another 5,000 years, all of this may be gone. Yeah, and we see this multiple times, and in fact, I found more than 12 of those large landslides in the Sutlej Valley. So this is a very dominant process, and they are all similar in timing. So they are not stochastically distributed. They all fall into those wet periods. So that's why the interpretation is that climate has to do with causing the triggering conditions for that. Yeah?
Would there be a certain scale of deposition or length of deposition along the river valley or thickness of such deposits where you would start to consider whether the detachment limit model remains valid or such equations of bedrock incision can remain valid? Because if it gets filled up to a very thick extent, essentially the river bed is so much more mobile.
I mean, so I have reconstructed the profile without the landslide based on bedrock outcrops down here, bedrock outcrops down here, and drilling holes. So there have been drillings done in the lake sediments that eventually reached bedrock at some point. So using those points, I have essentially reconstructed what the profile was like before, and I estimated the amount of sediment volume that has been stored throughout the landslide. So there is significant sediment amount that has been stored there. But yeah, that's certainly, you know, that I always refer to this as a transiently stored sediment. That certainly plays a big role in the sediment budget of the Himalaya. You have, you know, sediment that sits up there for a couple of thousand years, and then it gets eroded and gets transported down. You know, through a combination of field observations and additional geophysical observations, you can reconstruct the thickness. But of course, there are some uncertainties and stuff. Another thing that I did is I knew the valley shape. So if I do a cross section here, right, this is a glacial valley. This would be this valley. So I knew that this is the landslide deposits. And I essentially took, I have topographic information from here to here, right? And I just interpolated those until I reached the bottom to see what the original bedrock profile has been. Yeah. Okay, should we briefly talk about the chart plot stuff? Yeah? So again, when we made this figure, we really only had nick points in mind, okay? So Al and I, we were just interested in mapping nick points, and we did it on the Santa Cruz Island, but you can use that algorithm for pretty much any other area again. So this is a plot that conceptualizes distance upstream elevation. So this is a longitudinal river profile, okay? And we see that this dashed line would be the perfect exponential river profile, steady state conditions, okay? And if we have here a nick point on top of it, that's essentially a stretched version of what we just looked at, right? So if I'm pulling out, let me get this guy. No, this is the chart plots, not this, sorry. Where's my river profile? So let me just make this a little smaller. So what we are looking at here is essentially this nick point is a stretched out version of this guy here, right? So we have a steeper section. We have a steeper section and a flatter section, right? So this is this section. So we consider this point here is the top of the slope, the nick zone break. So this is where the nick zone occurs. And then we also can measure the vertical step. So we can say, for example, for the next nick point, the vertical step from here to here is the nick point height, right? So those are informations we can take off the longitudinal river profile, and we would have the same information in the chart plot, right? So now this dashed line, our exponential function, is a straight line in chart space, right? We talked about this yesterday, right? We are essentially unbending the river profile. We're integrating over the distance. We are unbending it. So this straight line is the same as this dashed line, and now it is much easier to see the magnitude changes because we have corrected for that bending, right? So now we can see we have a steepening zone and then a slightly less steep zone, and that distance from this line can also be considered the nick point magnitude. So we can directly measure it from that reference profile. And here we have two nick points. One is one has a longer wavelength, but a smaller vertical step, and this is a much shorter wavelength, but has a higher vertical step. So that's pretty much exactly what we have here. Wait, what we have here. Here we have a very large wavelength change, and here we have a very small. Over a short distance, we step up by 400 meters, okay? So this is a very high vertical step, and this is a slightly longer wavelength approach. So what we then have done here, and that other people have done this then too, we can just take that reference profile and detrend the data. So we just say, we take this line and rotate our river profile onto a straight line. So we are now looking at those ups and downs that are essentially the ups and downs along that profile, but we are not looking at it along the slope. We have detrended it. And now we can directly measure the magnitude, the distance of this line. We can determine where we have the nick zone lip, we call it, the nick zone length and the nick zone height we can directly measure of this plot. so we measure it in chi units, and we can convert this back into real topographic units because we know what the integration factor was, okay? So you can envision that by converting your data, your topographic profile into the chi profile, we can more easily do this detection of nick points because we have unstretched the profile, and then we see where we have the lows and highs of the nick point, and that is something that works out very well to identify nick zones. If you're interested in this, and if you have a tectonically active region, let me just point out that we have this code. I thought so. Let me. Yeah. We call it the nick zone picker. So on GitHub, it's a code that we call the nick zone picker. That is a code in Matlab that automatically identifies the nick points. It runs through your steps, and this is something that is based on the code that Al Neely and I have developed. So this is, if you're interested in this, you can look at it, and you also get a lot of output that can be then plotted in ArcGIS, for example, where the nick points are, if you have that, if you're interested in that. Okay. Any questions, thoughts, comments? So essentially, this is our last exercise that we do together. I just want you to be able to load data into Matlab and start with the first steps of the analysis, like as we have done. There's, of course, much greater depth that you can do, but with those simple codes, I think you can get started with your own digital elevation model. If there are no questions related to Matlab and DEMs, we could move to the LandLab exercise, or if you're interested, we could look at the ALOS DEM for the same area, or you could do this yourself, and we do the LandLab now. Yeah.
This script is not running actually. It is showing some sort of error.
It's not working?
Yeah, it's showing some sort of error actually.
The variable name should be Baspa and not Northwest Himalaya. I don't know why this is the case. This should be, oh no, this is Baspa.
Baspa only. I have changed actually.
Okay. Run it. Why? Can you go up? I can't see the error. You always have to look at the error.
Like matrix dimension.
Can you go up a little? I can't see the full error. Okay. Can you rerun maybe parts of it? I think. Have you run all through the steps? Yeah. Can you hit run again? I'm certain that. Oops. What is this? No, you changed something. If you use the code, I'm certain it works with the code that is provided. I think some things have not run on the way. You need to look. Can I see the code that you downloaded from GitHub?
Yes.
But that's not the code from GitHub, right?
Yeah, this is a code from GitHub.
Yeah?
Yeah.
Okay, then run it. Why is it not this? Why does it have a different name? Let's run it. Let's run it. Yeah. So can you make sure that you have that you're in the right directory?
Yeah, right directory. Baspa is saved in actually test Matlab, so it's open here also. Yeah, it's test Matlab.
Okay, but somehow it can't load it, right? Is that the? It doesn't find the
The
file.
same thing is happening in S also.
Let's focus on this. I mean, are you in the right directory? You know, now we are doing the debugging, right? Now, go into the directory. Can you type an ls down here? ls, ls, return. That means just list. Return. So there is your DEM. Can you go up? This is BASBA, Sediment. Okay. Can you do those two lines? Why?
This one.
Yeah.
You need to.
Yeah, you need to use single quotes. Use single quotes.
Right.
Use single.
Yes.
Type no. Type it in here. Do it always in the editor.
And there.
Okay, now let's select this again.
Okay.
Then do the next step.
Next is this one. So I'm just evaluating.
Yeah, I think it will work.
It's coming.
And now you can do complete. You can do now.
I think it's coming. No. It's
Yeah, let's go through it step by step. Yeah, you don't need the figure. That's just you don't need that.
so running up to this.
You don't need the figure. Okay.
Figure is coming. Then after
Then you do this, yeah.
area calculation. Up to this.
Yeah, you can select more too. This is
I can select like this.
More.
Sure.
yeah. I usually use a control return to go through it, right? If you I mean you do it the way you want it, but if if you go down a little, now you have this, right? You go down a little. Here, can you click in here? Click and do a right mouse click. Just the right mouse click. You see, here is
Evaluate current section.
evaluate current section. Then it does this entire section.
Okay.
Yeah.
It's working now.
And then you go to the next section.
Next section. Next section. Or
Next, go further. Next section.
Or
Here is the next section.
Right.
This is the next section.
evaluate current.
And you do the same exactly, and go down.
Figure. Yes.
Yeah.
So, right click.
Evaluate current section.
Yeah. Okay, it's gone.
Okay, you see it's coming together. So this is always go back and try to backtrack and debug. So yeah.
I'm having an error in this command.
Well, if you go do the command before, something is missing, right? So. And then do the next one. Something was missing, right? And then try this, yeah? I think one of the, can you click on this and this? If the variable, so then if there's an error, not look at the individual variables. Look at the individual variables to find out where the problem is. The variables are best by x and best by y. You type this in and you see what they look like. Are these the coordinates that you expect, for example, right? Because there's an error associated with the coordinates. And then you try to dig in there. Yeah? So.
I have error in this chat plot. Error in chat plot.
Can you go up? This is the error is in here. Yeah. I think I would rerun stuff. I see it should. I think some steps have not been. Is it working for you? No. 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 Let me see why it is. I would then put an updated code on So look at that. You have the Baspa River. If you click on those individually, like with the right mouse click, evaluate. You see if those have been constructed. Okay. I'm surprised that this is. Let me. Maybe you re-download the file from GitHub. So if you go to GitHub and you go to the file, I show you how you can download the file. So when you go to Matlab, and here you have this file, you can, for example, click on raw. Then you see the raw file, and then you do the right mouse click save as, and now you save it as now it also has a name, the Baspa steepness index. It's from that web page. Okay. I think one of the variables may have not been generated on the way. That. So, quick question: are you able to generate the chi plot and follow through, or are there? I know that there have been some issues, but I'm certain this is related to the code. Could you generate the chi plot? Yeah. Okay. Yeah. Maybe re-download the code. Then that may be the. Okay. My suggestion for the last 45 minutes or so is that we dive in. To LandLab again, okay? Just because we may learn something from doing landscape evolution modeling for the very same area. So there is, if you go to the web page. And you go into the LEM directory, you see that there is a code that is either a Jupyter notebook. So if you could follow it on a Jupyter notebook. I also generated a PDF. So if you're lost, look at the PDF. Okay, that's one thing. And the other thing is that we are now doing is we are following the code LandLab Baspa from DEM. This is a Python code that we work with in Spider. You could do the same in Jupyter Notebook either way. And if you're lost, please also look at the Baspa LandLab modeling from a DEM. This is something that you could almost do on your own because it's a commented PDF. You will also need the TIFF files in here. I suggest that you get the whole folder. That's just the usual thing you do on GitHub. You need to go into your Anaconda environment again. I'm going to open up Spider, and I will talk you through the different steps. I wait till everybody has the file open in Spider, yeah, and then we go through it. You may want to change the directory to where you have downloaded the DEM. Because we need to open that geotiff file. The file that we are open is bastbar_hydrochat 500 meters UTM 44 north WGS 84 clip.tiff. This is the file that we are going to work with. Are you able to download the two files? Is this going too slow? Should we copy it on a USB memory stick? Is this? Let me just say a few words of caution when you prepare this. So we are now going to work with a topography that we read in directly from a digital elevation model. And there are a couple of things that you need to carefully consider. And the first thing is when you get your hydroshed, your SOTM, or whatever DEM you would like to use, and then first of all, you need to reproject it to UTM coordinates, because you want to have units in meters as a spacing, because the units of height are in meters, and the units of diffusion are in meters, the units of stream power erosion are in meters. You can't have units in degree as distance units. And because you want to make sure that every grid cell has the same area, right? Because we are looking at drainage area too, so we can't have this. What is really important, when you clip your DEM, you cannot have any border that is no data or something else. Yeah, you need to have a raster, a rectangle, that is directly only covering the model area. We can do the thing that we just did in Matlab, where we clipped out an awkward shape, and then we used the largest connected components to clip out the river profile. We can't do that in the model domain. In the model domain, we have the model domain, and we cannot have a border around it, because the border values are usually very different values. So if you look at this, this is the first clip that I generated. This is a clip that I did from the original data, and you see it's slightly oblique. And what this means is that when this is no, I'm exaggerating. This is the clip. This is still being stored as a raster. This is still being stored as a raster in this rectangular form. And everything here is filled in with -999, because this is the no data value that is usually used. So you have elevations essentially surrounding this grid that have values of -9999. And that would be devastating for our model, right? Because you suddenly would have the largest Nick point ever, right? From plus 3,000 meters down to -9999 meters. So the LandLab cannot deal with no data values. LandLab needs to have values associated with every grid cell, yeah? So please make sure that when you clip your own area, that you have a clip that looks like this. So this is a nice rectangular clip. I just reclipped it to a rectangular clip. Excuse me. And this is the TIFF file that we can now load, because it doesn't have any border value. This is really important. Otherwise, you get really weird artifacts when you run it, because LandLab then thinks the river would drop down 10,000 meters. And of course, if you drop down 10,000 meters, that's a huge Nick point, so you will be eroding things very awkwardly, okay? So you will need to spend some time preparing the data. And then when you clip this, make sure that you have always exactly the same X and Y coordinates, and you can do that in QGIS by manually punching in the UTM X and Y coordinates, okay? So you know how to do this, right? So that you have the proper clip, that the clip is perfectly aligned. So let's assume you have that. You have this nice clip. Make sure that the resolution is somewhat reasonable. So right now, I'm working with a DEM that has 216 times 120 pixels. It's 500 meters. This may sound very, very low compared to what we just did, but keep in mind we are doing forward modeling and we want to get results in a reasonable amount of time. So if we would use a 1,000 by 1,000 meter grid here, we would still sit till in the afternoon, and I just don't want to do that. So be aware of the fact that this size of the grid essentially ends up determining how well you can or how fast the modeling is being performed. My suggestion is always to choose a coarser grid to start out with, twist and tweak the parameters until you feel happy. Then you can always load in a higher resolution DM afterwards, because it will exponentially take more time. So when you go from a 500 meter to a 250 meter DEM, you essentially increase the factor of time by at least 4. And then if you go down to 90 meter or something even better, you are at least 10 or 20 times as much as the original timing. So please consider that. So having said that, let's go into Python. Does everybody have Python open and ready to run? Okay, then just a few words here. In the model setup, we load the flow accumulator, fast gap eroder, and we do the linear diffusion model. Yeah, so these are the main parts that we are using. And here I have added a little function that I wrote to directly load in GeoTIFF files. So LandLab does not allow to load in GeoTIFF files. It allows you to load in ASCII files, but working with ASCII files is really, really awkward. It gets, you get large files and it's just awkward. So I wrote that little wrapper here that loads in a DEM file and puts it into a raster grid. So with that, you are able to directly load in the DEM. And the way this is being called, so you would go from here to the next line. You do the run cell in advance. So you have this loaded, I have everything imported, and then we can go through it one by one. So the first command is defining the name, and in the next command, I'm loading the DEM. Oops, I was too quick. I didn't want to do that. I'm sorry. Maybe I should sit down. I can see better that way. I am now evaluating. Why? I'm now evaluating this, and I'm loading in my data into the MG. So MG is my model grid. I have, if I open up my model grid, oops, I'm sorry, I'm just realizing that this is, oops, that this is too small. Let me make this bigger. So I have now loaded in the model grid, and here you see the information. My model grid is 105 times 166 grid points. We just had that, right? We just looked at this. And we have a spacing of 500 meters. And I actually have ignored the lower left spacing, because if we put UTM coordinates there, it would be minus 900,000 and plus 3 million or something. We don't need that. So it's always good to verify that this has been loaded correctly. One of the things that I'm providing here is I'm providing the geographic information so that you could also save the output file to a TIFF file. So in other words, when we have run the model, you can save the model grid to a TIFF file, and you could put it into an ArcGIS or QGIS and visualize it. Yeah. So for that, you would need the GT and CS parameters, because these are the original projection information. That just as a side note. So here we are setting up the further information, and we set up the boundary conditions. And I am leaving everything open. So all sides, right is closed, false, left is closed. I'm leaving all borders open, because this is real terrain. Things can go left and right, and top down. So we are not limiting any transport. And here, this is usually a nice thing to do first. Plot the figure to make sure that we have the proper terrain. So this is now the model domain. And seeing this, we know that we have properly imported it, and importantly check that these boundary points are not 0 or any weird condition. This looks okay. It looks a little coarse, right, compared to what we just looked at. We just looked at a 30-meter spatial resolution of the same area, much nicer focus. But again, we don't want to spend hours doing the forward model. So again, this is the Sutlej, this is the Baspa Valley, and down here we have the tones and the Parvati that we looked at yesterday, okay? So this is our model setup, and the next step is that we define the linear diffusion, the flow accumulator, and the fast-scape eroder. So we are setting the conditions for this. And now, keep in mind, what we are now doing here is we are setting our M over N, our setter, to 0.5. And here is where you could put in your information from that analysis that we just did. Here we could say that our M and N, essentially the M over N ratio that we determine, what do we say it is? 0.2428, right? Okay, so we say our M over N is equals 0.28 from the analysis that we just did. So, right, here I still have the standard values in it. We could now consider, we leave S, the exponent for N, the exponent for the slope is N, and the exponent for the area is M. We cannot easily determine those independently, but we can measure the ratio of them. My suggestion is that we would change that M to 0.3 or something, because we have measured this from the DEM, yeah? again, this is something that you would need to play around with a little and vary, but we know that we definitely don't have an M over M ratio of 0.5, because this doesn't fit with our data. Okay, now of course I need to initialize this, right, because I changed the parameters. And what I'm also doing here is I'm using an addition that is available for Landlab. There is a module that does the Chi analysis, what we just did in Matlab, and it does a steepness analysis the same way as we just did it in Matlab, but based on a stream power erosion law. So when we initialize the steepness finder, we use our input grid and our reference concavity. What are we going to choose here? Should we use a reference concavity of 0.3? So I'm just saying that we have measured, what was it, 0.28, right? We just say this is 0.3, okay? And we use as a reference concavity 0.3. What does that mean? That our slope in a log area, I must have drawn this plot probably a dozen times, right? Anyway, we have a theta of equals 0.5 is a standard, or 0.45 is a standard. If this is, actually this is minus 0.5, and if we have minus 0.3, it means that our theta is a little less, right? A little less steep. So we would have something that would, the overall slope of that terrain is less steep, or the river profile is less steep, because we have the landslides in there that essentially prevents the incision. So we have a concavity. It's not as concave as we want it to be. So in other words, this would be the original profile, and we have a profile that maybe looks a little more like this, where we have a lower theta, right? And the reason for this lower theta is the landslides that have filled in the valley, and therefore they're reducing the concavity, okay? So it's not as concave as it should be. It's less concave because there's sediment sitting in there, okay? And that, of course, will drive the erosion. But this is a parameter that you probably need to play around with. Okay, next. We set the rock uplift rate. This is something that is derived from thermochronological data. This is based on appetite fission tracks that Rasmus Tide did a few years ago, or many years ago. And we just assume an uplift rate of 5 times 10 to the minus 3, which is, what is it, 5 millimeters per year. Yeah. Probably it's probably a little less. Probably we should be around 1 millimeter per year. But we can check. We would need to do many model runs anyway. But just let's leave it at this. We do it in time steps of 1,000 years. We then multiply the rock uplift times the time step, right? So if we have a rock uplift rate of 5 millimeter per year, we do it in 1,000 year time steps. We would have 5 meters uplift per time step, okay? So this is the rock uplift length, and we want to forward it for 500,000 years. 500 time steps, 500 times 1,000 means 500,000 year model time, which means 500,000 years, okay? You can change it the way, so when we initiate the for loop, we go through those 500 steps, we add the uplift rate every step, spatially constant uplift rate, so we are not getting fancy here by adding a fault or something. This is just the constant uplift rate. Everybody who has been there in the bathbar knows it's not a spatially constant uplift rate, but let's just assume we do it that way, okay? We have the linear diffusion. Because we need to flow route for the fastscape erosion, for the stream power erosion, we need to do the sink filling. That's the same that we do with the digital elevation model, right? So we need to do a sink filling. Then we need to do the flow routing. We need to do the flow routing every time step because the topography is changing at every time step, right? And we do the fastscape eroder. And the fastscape eroder uses those coefficients up here. And then I'm printing every, I could also say I'm printing every, only every 50th step or something. I think that would be sufficient. And I think we maybe want to set this to 1 millimeter per year. But I think it's more realistic, okay? Okay, so having said that, we can run this part. You see I'm doing the same that I'm usually doing in Matlab. I'm selecting something, I'm hitting right mouse click, or you hit F9, and then you run the columns, the lines that you have selected. So I usually don't type in this window, or sometimes I do. Okay, now I am seeing the output. Only every 50th time step of the model step we see an output. And we know that we do 500 steps. So we are now at 200, 300, 400, 500. So again, the reason why we use the coarse resolution is that we can do it relatively fast. Otherwise, we will be waiting 10 minutes for the results, and there will be no fun either. We do the steepness and chi calculation on the resulting topography. You know, if you would be interested in looking at the evolution of the chi and of the steepness indices, you would need to put that into the for loop, right? So you could, excuse me, you could do this analysis, or you could do the steepness calculation for every time step and save it in a separate variable. We are currently not doing this, but you could. So let's look at what the topography looks like at the model output. Let's look at both. This is our initial, and this is our resulting topography, I think. And you see that we have, this is, by the way, the same scale, the same color scale. Yeah, I'm scaling it to the same minimum and maximum values so that we better can compare it. And you definitely see that because we used a still fairly high uplift rate and maybe a slower erosion rate, essentially topography is growing. You see less blue and red colors, blue and green colors in here because essentially the topography has been growing, right? The topography has not been incising. So the lower part of the Sutlej here is blue. Here it is not blue because it has been uplifting, okay? So we can argue about if that is true or not. We may want to adjust the erosion rates and the uplift rates a little more. We definitely see that the surrounding peaks have been increasing in elevation, okay? So that we, of course, have continuous erosion that occurs here. But that those peaks are really rapidly growing. You see the white colors in here. So these are strongly growing, partly due to the reason that we only use diffusion and fluvial erosion. We are not using any glacial erosion. And potentially the diffusion that we are using is a little too low, so that some of this is not being properly captured. So let's look at some of the other model outputs and then revise the parameters, okay? So another thing, nice thing to look at is usually the drainage area. This is the drainage area, and as we expect, we have no drainage capture or no change in the drainage area, so this is all fine. If we look at the steepness index, so we are now looking at the steepness index, you note that we cannot make as nice figures as we do in Matlab, but nevertheless, I think we all know what we are looking at. Here is the steepness that goes from 5 to 50, I think. Keep in mind that because we use a much coarser resolution of the digital elevation model, we always will have a lower slope angle. So using a 30-meter DEM, you always have steeper slopes than a 500-meter DEM. So we expect the overall steepness indices to be much lower, right? Because the overall slope that we have is much lower in a 500-meter DEM too, right? So it's not too surprising that the steepness indices are very different from what we have done before. Also here for the steepness index, I think we use the reference concavity of 0.3 and not 0.5. So we can change that as the next iteration. Nevertheless, I wanted to point out that part of these higher channel slopes or steepness indices that are associated with the landsliding, they have been eroded away. So some of those have been flattened out because you essentially have removed that first nick point that existed in there. Not surprisingly, this is what we expect to see there. I don't know if this would be useful looking at the Chi index right now. The Chi index is essentially, I don't think we need to discuss this. We do this at some later point. Let's do the following. I suggest that we revise some of the parameters and that we say that the steepness index that we calculate actually uses a reference concavity of 0.45. We continue to let the Fastscape eroder, or if we would set this to 0.5 and run the model, or you know what, I should keep my old topography open. I'm keeping this plot open, okay? And I'm going to change the parameters, and then I'm going to compare the topographic evolution, okay? So now, you have to reload the DEM because you have to reinitiate the model grid. We have to load the original topography on top of it, and then we run the model again. Otherwise, we would continue at that state that we are currently in, right? But we want to start out from the initial conditions. So what does this look like? And now that I have heavily increased that area exponent, and I set it to, where is my other figure? And I set it to 0.5, meaning that I make the rivers much more erosive, really, really much more erosive. Remember, that's a power law exponent, so it's a logarithmic scaling that goes in there. And now we see that the evolving landscape, that you really have a river valley that has eaten in the topography and have leveled down the topography by, it removed 2,000 or 3,000 meters of elevation because we have told the model to be a hyperactive river erosion. So, we know that this is not true, and we also know that this exponent that we have in there is not true, but we only know that it's not true because we did that Matlab analysis before, right? If we would have used the standard 0.45 or 0.5 approach, like these are the default values, we get a result that is not meaningful. Yeah. So this is why it's important that you do steps before you actually go in there. So we go back to our old value, which was 0.3, and we can think about linear diffusion for a second. I think this is a very low linear diffusion. That I was using a linear diffusion that has been measured on the Tibetan plateau. I mean, we are at the border of the Tibetan plateau, but this is not Tibet. Tibet is even more dry. So I'm slightly increasing the linear diffusion, and maybe another thing to do would be to do the modify the uplift rate, but I think this is a fairly good average. And by the way, the K value that I'm using, the K value, this is something that has been used for granitic rocks before, and we do have mostly basement gneissic granitic rocks, but I think it's even a little stronger. I think the rocks that we have in the higher Himalayan crystalline are stronger than the average granite because they have been, partly migmatized afterwards. So again, these are all information that you take from your field area. These are all information that you need to put in there. A modeler without field experience will never ever be able to reconstruct this in a meaningful way, right? Of course, you can change the parameters and then run the model 100,000 times, right? Until you get a good match with what you expect. But it's always better to start out with a parameter set that is meaningful. And those meaningful parameters always come from the field observation. So what are we looking at now? This now is our topography this is our topography before. This is before input, output. We still see that we have fairly high peaks here, but overall speaking, we are doing a pretty good job in capturing the overall valley. Some of the valleys are being deeper incised. Things that you could do now, you would look at the longitudinal river profile and you would see how the shape of the longitudinal river profile evolves. For example, how long does it take until that landslide has been removed, until the river profile has been made more steady state-like? So those are steps that you can do so that you could essentially forward predict some of the evolution, or alternatively, that you backward predict some of the evolution. You could also do the modeling the other way around. You could subtract a certain elevation range from your model and then forward model it to the present day, for example. So, or you could do a model scenario where you place a landslide or additional landslides in there, and you see how long it takes for the model to remove those landslides. You could essentially create a late Pleistocene topography and forward model it to the present day. Because at the present day we know exactly what the landscape looks like, and then we would see what it looks like in the past. So there are different approaches, but these are the first steps at least. Yeah? Now you would need to dive in, play with the parameters, and usually what you do is you run a range of parameters, and you are generating some kind of a misfit factor. So you would be running, for example, K, you would vary K, you vary M, you vary N, you vary the diffusivity, you vary the uplift rate. Obviously there are many things that you need to vary, so you end up having several models. And in the end, you are generating a misfit versus a present-day topography, for example. In other words, after every model run, you're looking at for example, you're looking at the delta H of topography in minus topography out, and that gives you an array, and you would then take, for example, the standard deviation, for example, right? The standard deviation could be one parameter, a misfit for every model run. And then you could rate every model that you have produced and compare the model output. So when you would then make a plot where you say, for example, K varies from, let's say, 1 times e to the minus 4, no, 1 times e to the minus 5, and here you would have the delta H, or potentially the standard deviation of delta H, and you would see how that varies, so you get a feeling for what is the sensitivity of a parameter. So some parameters may, for example, when we change the linear diffusivity, some parameters may only vary a little. You know, you may only see a small little change. So these are parameters that will not be very sensitive. We just changed the M to 0.5, and we saw a completely different topography, right? So for that setting, that standard deviation would be very, very large. So we would have a setting, if we would do this plot for the M value, that maybe goes from 0.3 to 0.6 you would do or something, you would see large differences in the model outputs, okay? So you need to do this kind of a sensitivity analysis to get a feeling for what are parameters that are very, very sensitive and what are parameters, you know, if we change the linear diffusion but from even from 0.001 to 0.01, so an order of magnitude, if we change the linear diffusion of an order of magnitude, the model results will not be that different. Okay, so that is a parameter that is not very sensitive. But if we would change K, or if we would change M, the model is very sensitive to this. So as an example, if we now do K, so let's say from 1 times 10 to the minus 5, we go to 5 times 10 to the minus 4. So we change it by a factor of 2 only, okay? And we leave everything else the same. If we then run this guy, so we are essentially making the rocks less erosive. So 1E5 means the rocks are fairly solid, granitic rocks, and now we are going to slightly softer rocks. So if we look at the output here, you know, now we have a landscape that has been almost fully beveled down because we have used sandstone-like lithology. Okay, so we use a lithology factor that is very, very small, and we see that essentially all the relief is gone, right? Everything has been smoothed down a lot because we used a different parameter for the rocks. Okay. I mean, you know, you probably would not change this by a factor of 2. You would only subtle, very little change it, but that would be the effect of it. Okay? Good. We have a few minutes left, and I first ask, you have any questions regarding this modeling exercise, or should we discuss things in more detail? Are there any points that should be discussed or reiterated? Yes?
If we take a flat topography and we try to evolve and match with the present day topography, so how to choose the flat topography? I mean, what should be our initial condition?
I mean, this is similar to what we did 2 days ago. You mean like a plateau region or
Yes,
something,
exactly.
a flat turf. For what topography you mean? For
So suppose if we have the flat topography and we are trying to like replicate the same what we see in the present day. So how to get those topography, like final topography from the present, I mean from the past?
I'm sorry, I don't think I understand.
So the question, if I can rephrase, the question is how to constrain initial state to be given as input in this model. So we have an initial state and then we are evolving that through time. Right now the initial state is the current topography that we have. If we want to know that how this current topography is there from a paleotopography, how to constrain that paleotopography?
I mean, are you asking me how to put in a different grid as initial condition?
Yeah. Yeah. Maybe.
Well, that's what we did 2 days ago, right? So where we had, for example, if you look at GitHub, in the landscape evolution modeling, we have that, for example, the Gaussian hill, right? The Gaussian hill is a different initial condition, right? So if we would look at that Gaussian hill, we can generate a grid with whatever topography you like, a plane, a flat surface, and then you just add it as a field. So this would be here the command where you then add the raster topography as a field. So instead of loading in a geotiff, you can use any array that you produce. And you can make the array the same size as your output DEM, and then you could see how it evolves. So one for that particular example for the Sutlej or for the Baspa Valley here, one thing that I would do before I wouldn't start out with a plane. I would greatly smooth this terrain. So I would, for example, run a maximum filter over it that takes a maximum of the 5 neighboring or the 15 neighboring plots. So essentially, when you have terrain, if I'm drawing a profile across the terrain, and you have terrain that looks like this, so this is the river incision, I would now say take the maximum elevation over a certain window and put that elevation there. So out of this real digital elevation model, I probably would make something like this, essentially something that is not incised. And you can do that with a maximum filter directly in NumPy. So you could load in, or you could use that NumPy grid of the topography and use a maximum filter or something that would greatly smooth your topography. Yeah, that would be a nice, interesting thing to do. Yeah.
Sir, you said the linear diffusion coefficient, it won't matter, the topography won't matter if you change it by an order of magnitude. But sir, my interest was, isn't that dependent on the uplift rate?
I mean, the reason why I said the linear diffusion doesn't play such a big role there is mostly that the terrain is really, really steep, and it's greatly driven by fluvial erosion. We, in fact, have only very little soil cover in those areas. So the linear diffusion would be very, very important if we're out in the Seawall Lakes or in some other area where you have a considerable soil cover. Here in the Baspa River, we have lots of bedrock exposed, so there is very little soil cover. So that was my comment why I said it doesn't matter much what linear diffusion you use, but realistically, you want to have a linear diffusion rather on the lower side because you have so much bedrock. If you would have soil cover, if you would have a thicker soil cover, for example, if you had a lower elevation where you have higher soil production rates, your linear diffusion would be much higher, much higher.
So I wanted to understand its relation with the uplift rate.
Well, linear diffusion in that sense is independent of uplift rate. The connection is given by the soil production rate. In other words, if you think or if you assume that uplift rate is equal soil production rate, then linear diffusion would become higher if you have higher uplift rates because you have a larger soil area that you could move down. The linear diffusion is a tricky issue here because we have so little soil cover in that area. So I always feel a little uncomfortable dealing with the linear diffusion in those areas because we know from fieldwork that we have mostly bedrock outcropping. And then linear diffusion is not an important factor for bedrock. You know, linear diffusion is for a soil mantled landscape.
So like if you have where you have higher elevation, your linear diffusion coefficient will be very less because you are exposing bedrocks. As far as I understand, if you have a little lower relief, lower elevations, here the diffusion coefficient that's going to be higher. But we are applying the one coefficient for the entire
no. I mean, I make the linear diffusion is just the amount of material that gets moved through a unit area. So you know, the linear coefficient is in meters per what did I say? Meters per year. And meters squared per year, and it essentially tells me how much material is moving downslope as a function of curvature. You're right that diffusivity would change as a factor of elevation because you change the temperature. You go from moderate to cryospheric conditions, for example, and in the cryosphere you have different processes happen. But we don't model this here. Temperature doesn't go in this model. There are other linear diffusion implementations that would allow you to do that, where you could specifically make linear diffusion a function of temperature, which then means that the areas that are above freezing, they continuously move, whereas the areas that are below freezing, they are stuck for a part of the year and they only partly move. You know, doing the soil-based linear diffusion, there are entire departments that do nothing else but linear diffusion on soils. It's a whole world for itself in that sense. I think you need to determine for your field area what is realistic to implement. Because you know there are landscape or there are soil development models that take into account different chemistry, different water amounts, different vegetation cover. You know, there's an indefinite amount of detail that you could add here. So you know, for that reason, most of the landscape evolution modelers that are in tectonically active regions, they mostly use fluvial erosion because the argument is fluvial erosion is driving pretty much everything. So that's part of the argument.
Thank you, sir.
Yeah.
So let's say when I'm saying only for the shivaliks, so how do we have to go to field, and from there we have to determine the diffusivity and then the K. And is there any modeled parameter like what we can set for the shivaliks?
For the shivaliks?
Shivaliks, yeah.
I mean, in order to get a diffusion coefficient, you need to do dating of known surfaces and then look at how they evolve through time. So a very typical thing is fault scarp dating, right? If you would find a fault scarp in the shivaliks that would look like this, you know this is the original fault scarp that has been formed. You do OSL or CRN dating of those surfaces, so then you know what is the age of the fault scarp, and then you so this is the original fault scarp when it formed, and now the fault scarp may look something like this, right? So you take the very detailed topography with a terrestrial laser scanner or with a total station, and then you use the linear diffusion model that we had explained 2 days ago, and you backward solve for the kappa. So the kappa is dependent on the second derivative of the slope, the curvature, right? and we have the age. So we have the timing, we have the topography, we know the initial topography, we can solve this equation for the diffusion coefficient, and then we have a linear diffusion coefficient. So there are studies that have done this on the Tibetan Plateau, on some of those fault areas, studies that have done that in Southern California. Tom Hanks is one of the persons that was active there. Eric Kirby did it in the Tibetan Plateau regions. So those are ways of determining diffusion coefficients. Another option is that you have fluvial river terraces. Fluvial river terraces form usually in a similar fashion. If you date this surface, you have cosmogenic nuclides or OSL, and then you look at the change in topography, how it changed, how it smoothened out, you can solve for that same equation. So these are some of the ways how you can determine linear diffusion coefficients.
But as per my knowledge, it's not done for the Shivaliks till now, like the
I actually don't know. I'm certain that there are dated surfaces and people could do that. But, I mean, again, the question is, if you have a single fault scarp, if you do fault scarp modeling, you definitely want to know the linear diffusivity. If you do landscape evolution modeling, I'm not entirely certain how important the linear diffusivity is for the Shivaliks.
Okay, for Shivaliks also, like we can take set any parameter, it won't change that much that you are saying. Okay. And what about that erodibility? That also we have to take from field
of sandstone, yeah. Sandstone. I mean, you can take other references from the literature where people looked at sandstones and different types of sandstone and use that as a K parameter. Yeah, you know, yeah. I mean, maybe I should have said in the beginning, the landscape evolution models are not there that you can realistically forward model a landscape. You know, we just have seen that you know, you can reproduce the general shape of the landscape, and we can look at some of the steps, but we are not going to realistically forward model the landscape. But we can ask certain questions. How do nick points evolve through time? How does a certain hill slope develop? You know, if you have very specific questions in your field area, for example, those nick points associated with landslides that I was showing earlier, you know, that would be a perfect study for a landscape evolution model where you would look at how long would it take till that nick point disappears, for example. You will not be able to realistically forward model the Shivaliks for 1 million years into the future. You know, at least not with that simple model. You would also need to take into account climate changes, vegetation cover. You would need to look into bedding of the lithology and things like that. So these model approaches are fairly crude. They give you an estimate, but they don't give you a realistic impression of the landscape, you know. So
can we use it to see the stability of the divides or the migration, like in which direction the divide will propagate?
Drainage divides?
Yeah.
Yeah, that could be an interesting topic. You know, that's at a large scale. You would see, you know, for example, you could then ask question. How important, or what is the importance of base level changes, right? If you have Shivaliks, and you know, you have a drainage system that comes out of the Himalaya, goes around. Sometimes it looks something like this, right? And here you have a structure that may be some kind of an anticline, right? Yes. And so you have, if you now would draw a profile across this, we would be at, you know, if you would have a profile across this, this is the height, this is distance, this is A, B, then this would look something like this, right? I'm making it a little oblique. And then you could model this by essentially looking how this landscape evolves, how it is decaying essentially. And you make this a function of the base level. So you're changing, this is one base level, this is another base level, you're changing the river height, and you could forward model by essentially putting in your model a different uplift rate. What happens to the drainage divide if you keep this stable and you lower this, for example? You could explore the effect of uplift rates if you keep the base level the same. So those would be very interesting questions. Yeah, if you think about that scale, yes, I could actually see that setting up a model for one of the growing structures in the seawall lakes that looks at the competition of base level change versus tectonically driven uplift. You could also then include a sedimentation part. In other words, you could then ask the question, what if you fill in, if this is a dune, like an intramontane valley, you fill in that valley, what happens? Because then the stream profile would get lower, which means that the rivers on this side become less erosive, which would mean that the drainage divide should migrate towards the mountains because these rivers are continue to eating into the bedrock. So those are interesting questions. So you're exploring the relative effect of different driving factors. That you can do with models very well. But again, you are then generating a set of synthetic environments and boundary conditions, and you're running this. For this, it works really well. If you realistically want to forward the seawall lakes, it will be more tricky.
Thanks.
So.
Is there a set methodology in the literature where we can use Schmidt-Hammer rebound values over a large area to get estimates of rock erodibility?
Rock erodibility?
Right. Rock resistance.
I mean, we have been taking Schmidt-Hammer measurements in the Baspa Valley. So the Schmidt-Hammer is a hammer that essentially has a little spring in it. You push it against it, and it releases. I don't think you can get absolute measurements, but you can get
relative R values. And
you can get relative rock strength measurements for gneissic rock, granitic rocks, and other rocks. It won't work well on sedimentary rocks.
So that's ecotip and.
But one of the things, I mean, we did the Schmidt-Hammer measurements in the field together in the Baspa when we were there 2 years ago, and the values are very variable. I would say it's tricky. But yes, there could be one way of looking at it. Yes, definitely would be a nice quantitative way. So.
Questions? Any more? No more questions?
Okay, I see that it's already 12:45. I don't want to deprive you of your lunch. Then maybe we have in the afternoon, or if there's interest, I could say a few words about, I've been asked from several people about landslide modeling, and I also talked about the importance of landsliding, right, the Baspa Valley that we just looked at. Maybe I say a few words in the afternoon about this, how you could model this and what are different approaches to do this. But I think we take a break now. Yeah? Okay.
Thank you, Bodo, for your work. Yeah, thanks. Thanks a lot.
No problem.